talk of Ariel about information principles for non-local correlations based on sequence.
Thank you, Glaucia. First, I'd like to start by thanking the organizers for the invitation to present part of my work here and for organizing this extremely nice event. So, I will start by giving an extremely brief introduction to Kolmogorov complexity and algorithmic randomness. It will be extremely brief. Why does the clock say 25? Okay, for the question time. Okay, then I will go to tell you what happens when you try to do Bell experiments with pseudo-random inputs. Then, if the time helps, I will tell you if nature can be at the same time non-local, computable, and non-signaling. And finally, I will show you something on how to go towards a geometric view on non-local correlations when it comes to sequences. So the broad view of this talk is to consider sequences of Bell-like experiments instead of just probabilities. The reason for this is first because this gives a broader view on non-locality, since when we only consider probabilities, we are erasing information. We have a series of experiments, and we just calculate the probability, and we try to analyze that. We are losing lots of information on how each single experiment went on. And second, because we can avoid some counterfactual arguments. This was on a paper by Stefan Wolf. Because when we talk about probabilities, we say that some different results could have arisen from the experiment we did. And all we measured was the probability of having that particular result. So actually, this implies that we think there were other possible results. And when we analyze the sequence of experiments, we actually analyze what we got in the lab without thinking about what didn't go on the lab. So let's begin with a little bit on randomness and Kolmogorov complexity. So I have these three sequences, binary sequences. Which one you think is more likely to arise from a fair coin tossing? Well, of course, the three are equally likely because they have the same length. So the probability is 1 over 2 to the n. Okay, I actually did the experiment, and I got one of these three. Who thinks it was the first one? Okay, the second one? The second, and the third one? Good, so no one thinks it was the first one. So these are equally likely, but no one thinks it was the first one. Good. Now the second one is the number pi written in binary. So I will ask you again, who thinks it was the second one? So there's one guy there who thinks I got pi in binary. That's extremely strange. I actually got the third one. So these are equally likely, but somehow you don't believe I got the first one. So not so equally likely. So what does it mean that the third one seems more random? Well, the idea that the first two have a name, like alternate 0 and 1 or pi, means that they are highly compressible. Okay? Because if I want to send some information to someone to reproduce that sequence, I could only have said, well, it's pi. I don't need to send the whole sequence. But for the third one, I need to send the whole sequence in order for the other party to reproduce. Okay? So this is the notion that captures algorithmic randomness. Algorithmic randomness basically encodes this information, how much information I need to send to another party in order to reproduce the string I have. So we basically say that if a string is incompressible, then it's random. Now, what does it mean, the Kolmogorov complexity of a string? Basically, the Kolmogorov complexity of a given string x, denoted by k of x, is the length of the shortest description or the shortest computer program that outputs x. So it's the maximal compression we can give to a given string. Okay? Okay, so it basically tells how much information that string has. For the number pi, there's a really short program that outputs any given bit from pi. So it's basically highly compressible in this sense. And one more notion I will need for the last part of the talk is the notion of normalized information distance. This definition here that involves the Kolmogorov complexity of y given x means that I have an oracle for x, and I need the shortest program that has free access to x, but computes y. Okay, that's what that means. Well, this notion gives a notion of distance between two strings with the property that this distance is equal to 0 if and only if the two strings are the same, and equals to 1 if and only if the two are independent. So this is the property I want for this distance. Okay. So now I will go on and tell you about some results we have on analyzing strings of experiments. The first one is a loophole that we did in collaboration with Gonzalo de la Torre, Gabriel Seno, who is here, Santiago Figueira from Buenos Aires, Antonia Sin. And the idea is what happens in a Bell experiment when we have pseudo-random inputs instead of random inputs. So you are all familiar with the Bell scenario. We will consider just the CHSH. The system is local if you can factorize the probabilities. And what we will do is to go to the known memory scenario in which we introduce an eavesdropper that prepares the boxes locally. Okay, it prepares local boxes with information on the former rounds, on the previous rounds of the experiment. That's why we need information on the sequence of experiments here. So it's basically this picture. After round 1, the eavesdropper prepares the boxes for the next round, and so on. On every round, the eavesdropper prepares the boxes. So the key idea here, if somehow the eavesdropper was able to predict the forthcoming bits from the inputs, either by Alice or Bob, the eavesdropper could prepare the boxes in order to give whatever probability she wants. Because once you know what the inputs will be, you can prepare boxes to give exactly the output you want for that input, and that's it. These are local boxes reproducing any probability you want. And this problem of predicting the forthcoming bits was a problem known as learnability of infinite sequences from prefixes. By seeing the first bits of a sequence, try to guess the next one correctly. And this was already studied by Solomonov, Gold, Zugman independently. So the key idea from learnability is that any time or space-bounded complexity class, such as P, NP, exp, any of those complexity classes, can be learned from prefixes. But it means that after seeing a long enough prefix from a sequence from a given class, one can start predicting perfectly all the forthcoming bits. And the algorithm to predict is basically this picture here. Since these classes, all the time or space-bounded classes, are computably enumerable, one can list the sequences from a class in order. So after seeing, I don't know, 3 bits, one goes to the first one that starts that way, and the guess will be the next one. And by doing that, one can ensure that at some point, one will reach the actual sequence that was used because it's one from the list. So if you make mistakes, you move forward on the list, and at some point, you have to reach the actual sequence that they were using. So with the assumption that the sequences are from one complexity class, one can learn and start predicting correctly the forthcoming bits. So with this in mind, the results we have is that if Alice and Bob use computable functions, of course they belong to some complexity class because every function belongs to one. So they cannot rule out an eavesdropper that is learning a class larger than the one to which the functions for Alice and Bob's boxes belong. So there's no way for them, if they are using some computable notion of randomness like any pseudo-randomness, the run function from MATLAB or whatever, to rule out an eavesdropper preparing local boxes. So any Bell violation they see, they still cannot rule out the eavesdropper. On the other hand, if you look from the perspective of the eavesdropper can choose what complexity class is learning. The eavesdropper can decide to learn P and P or whatever. And then it's forcing Alice and Bob to have to resort to harder to compute functions. So basically that eavesdropper, if it was an existing eavesdropper and not something abstract like nature, can force Alice and Bob to have to do extremely difficult tasks in order to see a proper violation of a Bell inequality. Okay? Good. So, as a second result, in collaboration with the same people from the previous one, I will try to answer this question. Can nature be at the same time non-local, computable, and non-signaling? Of course, you are all familiar with, I don't remember the guy's name, but whenever a title finishes with a question mark, the answer is no. You probably know about that. So the answer will be no. So in order to show that, we will use this kind of model in which we ask, how does nature generate non-locality? And we will resort to a model that has some hidden signaling between the boxes. That is, the boxes somehow communicate faster than light, but at a level that the observers cannot use that to communicate information. Okay, it's just the boxes sending some superluminal signal to each other. The only thing that makes sense to signal is the inputs, because later on we will assume that we have computable inputs, computable outputs. Therefore, anything that is done by one box is codified on the input, because the rest is just some computation from that. So the other box could do it. So there will be a hidden signaling of the inputs, and then at the outputs, what both boxes will do is to output some computable function, some function, A or B, that depends on both inputs and depends on the number of rounds. Okay? So of course, if we don't assume anything about the functions, we can reproduce any Bell experiment ever done by choosing the function. I mean, I pick the function that just gives the bits that they actually saw in the experiment. So this implies no restriction at all. The restriction comes from the fact that I will ask for A and B to be computable functions, which is something that is usually reasonable for classical models. Okay? Okay, so as I told you, both functions depend on each other's inputs, and we will assume them to be computable. So since we assume that when they calculate the probabilities, the relative frequencies, they show non-locality, this means that in infinitely many rounds, Bob's output will have to depend non-trivially on Alice's input, because otherwise they will obtain something which is completely local. Okay? So this function B has to depend non-trivially on the other party's input in order to show non-locality. Therefore, if Bob knew the function his box is computing, if Bob knew what function B is, he would be able to reconstruct Alice's input for all these rounds. Because on each of these rounds, by looking at the value of the function B, which is a binary value, he can know if Alice input 0 or 1. You see this? But the problem here is that B is a function that we don't know. It's what the box is doing. So we cannot assume that we know that function. So what can we do with that? This function B is nature's secret somehow. The whole idea is to use learnability again and try to learn the function B. So after so many rounds, we can know perfectly what the function B is. If we know perfectly what the function B is, then we are done, because on all these rounds, Alice can signal to Bob. So let's see how to do this, how to learn function B. The idea will be the following. Alice and Bob will pre-share a random sequence made up from the following symbols. Either it is a binary pair, or it is a number from 1 to m, each symbol from the sequence they share. So if the symbol for round n, the symbol in the position n, is a binary pair, they will use that pair, both Alice and Bob, as inputs for their boxes. So they both know the other party's input. And since they know the other party's input, and Bob can see his output, he will use those rounds for learnability. He knows all the inputs and the output, and then he will move on this list of functions from the class he's assuming his box belongs to try to learn the function his box is calculating. And whenever the symbol from this sequence that they pre-shared is a number from 1 to m, Alice will input the ith bit from her message that she wants to signal to Bob. So in all of these rounds, Alice will be putting on her input something for Bob to try to reconstruct the message. And the interesting thing is that if Bob's guess for B at some point of the experiment is wrong, since S is a random sequence, there will be one round in which he will know both parties' input, and his guess for the output will not coincide with his actual output. So we will know he made a mistake with that guess for B, so he will move on the list of functions. So at some point, he will learn the function. That means that if he's wrong, he will move on. Therefore, he will only stop moving on the list of functions until he finds the actual function that the box is computing. So the other question to consider here is that we are assuming that the boxes are computable. So is it fair to give Alice and Bob the possibility to share a random sequence? Doesn't seem like it. We are assuming that everything in nature is deterministic here. So where do Alice and Bob get randomness from? So in order not to get too technical, let me just tell you that there are some sequences that look like random sequences against an adversary that has some limited computing power. So since Bob has to assume that his box is computing a function from some complexity class, C, in order to learn, they could pick a computable sequence that looks random to an adversary with computing power on the class C. So basically, they can replace this random sequence from a pseudo-random one, and this protocol will still work. Therefore, what we've shown here is that non-signaling deterministic models for non-local correlations have to be uncomputable. If we want a model with hidden signaling and computable boxes, that won't work. They could use it to signal at the observation level. So the only way for these models to work is to have uncomputable boxes if they resort to hidden signaling. Okay, so as a final result, I wanted to tell you, when considering sequences of experiments, of Bell-like experiments, I wanted to tell you a little bit about how to define non-signaling and locality and what lies in beneath those concepts. So in that same paper I mentioned by Stefan Wolf, he defined non-signaling for strings the following way. If the complexity of Alice's output, now this is a string, not just a single bit, given Alice's input, is more or less the same as the complexity of Alice's output, given Alice's input and Bob's input, that basically means that Bob's input doesn't help Alice's box compute her output. Okay? So this is the notion that Stefan Wolf proposes as a notion of non-signaling. And of course, the same for Bob's side. So basically, knowing the other party's input doesn't help you compute your own output. That's what this means. So that's the notion proposed as non-signaling. And if we assume independence for the rounds, this reproduces non-signaling from the probabilistic view. So it's a reasonable definition. And now how can we define locality in this? Well, the reason for the more or less is because the Kolmogorov complexity is defined up to an additive constant, which is independent of the sequences. So this more or less means that you have that additive constant, but doesn't depend on the length of the strings. So if you divide one by the other on the limit of infinite sequences, this gives 1. Okay? But it's not exactly the same value. There's also one factor, which is of the order of the logarithm of the length of the sequences. Okay. To define locality, things are a bit more tricky because one needs to define somehow the hidden variables. But again, in that same paper, they give some definition that is reasonable, which is that there exists a string lambda, which acts as the hidden variables for the model, which is independent from x and y. This thing here means that x and y and lambda have no information in common, because lambda doesn't help you compute x and y in any way, so they are completely independent. And this lambda trivializes a and b. So once you have the hidden variable and you have x, you can compute a with no effort. And the same goes for b. So it's a reasonable definition for locality, which also, in the case of independent inputs, independent rounds, reproduces what we expect for local correlations. So the problem here, and I will show you some idea on how we can solve, is that this definition of locality and this definition of non-signaling lack of a geometric view. So we don't have something like a polytope and know how non-local something is and stuff like that. Just have the definition for local and the definition for non-signaling. So we want to look for some notion as more local than and stuff like that in order to be able to see what happens in between, to try to derive some theorems on like bounds when we talk about strings, and to keep working on non-locality when we have strings. We don't just want the definition for locality and signaling. So I will show you one proposal for such a notion, which is the following. We can rewrite locality and non-signaling as follows. A, B, X, and Y are local if there exists an omega, another sequence, independent from X and Y, such that this holds. This basically is just renaming lambda by omega. But more interestingly, we can define non-signaling in a way that looks similar to this locality, which is if we consider omega equals to X and Y, the definition for non-signaling can be rewritten as follows. K of A given X omega equals K of A given X, and K of B given Y omega equals to K of B given Y. So basically, this omega here acts as adding Y here, and this omega here is like adding the information from X. By the way, this is not a product. This is a concatenation of strings, okay? So this definition is the same as the one we had before, but algebraically modified in order to look more similar to locality. So with this in mind, one can write this function here, which is a function that depends on a sequence omega, includes the distance, the normalized distance within omega and the string xy, which we will use in order to say omega independent from x and y, or omega equal to x and y. That's why I put this normalized information distance here, plus k of a given x omega over k of a of x, which I use to distinguish when this value is 0 from when these two values are equal, and this other one here. So this function has the following property. It provides a quantification of non-locality and signaling when we are talking about strings. If the minimum over omega of this function is 0, that means that a, b, x, and y are local strings, are locally generated strings. And if the max over omega of this function is 1, that means that the strings are signaling. So then we can start moving around to see things that are more local than others and stuff like that, depending on how this minimum and maximum move. Of course, this implies optimizing over all sequences, which is an extremely hard task. But for some cases, we can go and try to reproduce the results we get from the independent view. If we assume that the rounds are independent, we can do some of these calculations exactly and see if it reproduces zeros and bounds and stuff like that. So this is still a tool. If equals 1, non-signaling. Okay, so we have a way to quantify non-locality and signaling. Of course, it's not simple, it's not computable, not only because of this optimization, but because the Kolmogorov complexity is not computable, but it gives a notion to work with. So as a summary, we've shown a loophole when analyzing obvious pseudo-random inputs for bell-like experiments. Then we saw that hidden signaling models have to be uncomputable if they want to avoid signaling at the observer's level. And finally, we provided an easy way to unify locality and non-signaling when we analyze sequences, not quantum. To analyze just that, locality and non-signaling when looking at sequences. So that's all.
Thanks for the talk. Questions?
Yeah, very nice and instructive talk. Unfortunately, I'm a pragmatic, and so